Hello and welcome to another edition of Physics 264 Pre-Lab Tutorials. I'm Dr. Steve Brule. Today we're going to study the 7490 binary coded decimal counter. First we'll spend a little time understanding the operation of this 7490. Well, the 7490 chip is a collection of 5 logic gates, 1, 2, 3, 4, 5, together with 4 JK flip-flops. And it creates 2 types of counters, a divide by 2 counter and a divide by 5 counter. The divide by 2 goes on input A, and the divide by 5 is relating to input B, as we will see. These pins are for different configurations that you can make the 7490 with, but we will not be doing that in our lab. Okay, let's first look at the function of the divide by 2 counter on input A. When the clock goes high, there's no change in the 4 output pins of the 7490. But when the clock goes down on the negative edge of the clock, we see that QA goes high. Then the input, it goes up high again, and this stays as it was. There's no... As you'll see throughout this video, there's never any change on the positive edge of the clock cycle, only on the negative edge. So now the input goes down, and then QA went to 0 again. Again, we go high, nothing changes, goes down, this goes up. You're getting the idea. When it goes high, there's no change. It goes low again, and the state of QA goes back to 0. So that's a counter. It counts from 0 to 1 on this pin. And why is it called a divide by 2? Let's see. So this has flashed once. This hasn't flashed at all yet. I'm going through one cycle here, going from 0 to 1. Now it's flashed. This one has not flashed. This goes down. Now we've flashed once with both of them. This one goes high again. There's no flash here, and it goes low, and now this is low. So you see that this is flashed once, or 2 flashes of the input A. So that's a divide by 2. We can make a divide by 5 counter if we use input B. So input B relates to these 3 pins, and we'll see this is the one that goes 1 flash for 5 flashes of the clocking of input B. Watch. So input B goes high, no change here. Goes low, we get that goes high. Goes high, there's no change. Goes low here. Now this has gone low, this has gone high. So this is counting in decimal here. You know, this is 2 to the 1, this is 2 to the 0, this is 2 to the 2. Okay, goes high, there's no change. Goes low again, now this one's up again. So now we've got 2, let's see, 2 to the 1. So 2 plus 1 is 3, so that would be up to 3. So that's a binary number for 3 in these 3 digits here. Positive edge of the clock going high doesn't change anything here. Input B's clocked low, and now these 2 went low, and this is high, and we're up at 4. So we've counted from 0, which was 0, 0, 0, to 4, which is 1, 0, 0. So that's 5 numbers. 0, 1, 2, 3, 4. There's 5. So that goes high again. This is still high, no change. So now we've flashed 5 times here for 1 flash of that guy. Divide by 5. And then we flash low again. I mean, the input of B goes low again, and we start the cycle once again for the input B divide by 5. Well, we could have this with 3 digits in binary. You could go all the way up to 111, which would be the number 7. But the logic inside the 7490 is nominally configured so it starts over after it gets up to 4. And the way it's configured, you studied in class with all those gates and so forth. Okay, we can create a counter that counts from 0 to 9 by taking the output here, QA, and feeding it into our divide by 5 counter there. So we've got a divide by 2 latching over here to the divide by 5. And watch, well, we're not going to go through that simulation. But if we did, we'd see this this pin, the indicator here, would be flashing on and off just like it would if you didn't have this feedback set up. And then input B is only going to clock once for every 2 negative clock cycles of input A. Remember, because we're getting a divide by 2 here, so it's going to count up to 5. It counts as 5 times, but only every other clock cycle. So in that way, we're able to count up from 0 to 9. I believe it's like this. It would be 9. So that's 10 digits. Okay, once so here's the counter. Well, how can we take this binary coded decimal output from the counter and feed it into a LCD display that we can then see with our eyeballs? We'll use a CA3161. Actually, in our lab, we're going to use a 7447 because Multisim doesn't have the 3161, which has its resistors built in. Anyway, don't worry about that. So this is the chip that drives the LCD display, and you just put the input to the chip in binary coded decimal, and then it figures out what display element to light up with its own internal logic. We just stick an oscilloscope here to monitor the clock cycle, and remember, the clock cycle only works on the negative edge. Okay, well, here's a few notes about setting up the circuit in Multisim. First of all, you'll need a 555CN chip. That's found in the mixed folder, and then under timer, then I'll go for the LM555CN, and then it'll look like this. Well, they don't give you the pinouts like we're used to using from last lab, but I provided them to you here. And here's the schematic that we used last week for our 555. And you hook up the this simulated chip just like you would with a real chip. You go through, and so pin 1 is going to go to ground, so I'll make sure that that goes to a ground. I believe we have to use a digital ground in this 555. So draw a line over that, so you put one of those in there. Pin 8, which is right there. So pin 8 of your chip will then go up to your +5. You'll have to have a battery that provides that, so you'll have to insert a battery in your Multisim simulation so that you have a +5 to go up to. Pin 4 is also high, so there's pin 4, so you put that up to the +5 rail that you'll create. You'll use a capacitor, and that's going to go on to pin 2 there. There's the trigger input of the 555. We're going to use a 5,000 nanofarad capacitor instead of the 2.2 nanofarad capacitor that's in the lab. It just works in Multisim where the 470 or the 2.2 microfarads with the 470K resistance does not work. Okay, we're going to use 2K resistors for these two resistors that are going to, one pin is going to go onto the pin 2, and there's a resistor. So you go through all that in Multisim. And so I'm telling you to use 2K resistors and a 5,000 nanofarad capacitor, but you can always change that around once you're in Multisim, because once you run Multisim, even though you have a time constant that you think you ought to see, Multisim operates on its own time frame, and it depends on how fast your computer runs. So you can adjust these resistors up or down if it's moving too fast or slow. Okay, then, still putting all these, pin 7, there's pin 7 is going to go to the junction between your resistors that you hook up in Multisim, and so forth. Put pin 6 to pin 2, so there should be some kind of jumper in Multisim that does that, and then that pin goes to here. Alright, so you're getting the idea, and pin 3 of your 555 virtual chip will then go over to your counter chip, your 7490 counter chip, which is found in the TTL folder inside Multisim. These are a little bit tricky to find, so I spend a little time finding them myself. So that's what it'll look like. Notice that the power and the ground that the chip itself works on are not shown in Multisim, because Multisim figures out it's running it in a virtual world. You don't need to power it, although some of the chips you do. So it's a little bit hypocritical, really. Multisim does not have a 3161 7-segment display driver. So we're going to use the 7447 instead, which works the same way essentially as far as you're concerned. In real life, if you were using a 7447, you would have to have resistors to limit the diode that's in here, to limit the current. But the yeah, that's right. So the display driver of the 3161 has those resistors built in. This one doesn't, but Multisim doesn't care. So you don't, in real life, you would need those resistors, but not in the Multisim world. Okay, and finally, you'll need a 7-segment common anode display, which is found in the indicators folder of Multisim. So there it is, and you can pick if you'd rather use a blue or green or orange. A little bit of variation is permitted. Use the digital state probes found in the indicator probe folder to display the output of your 555 timer. So I was using a newer version of Multisim where they allow you to make your chips look like real chips, although they wouldn't let me do it there. But I just thought it would be fun to do a real chip and let you guys do the one that looks like a simulated chip. But you can find the 555 simulation in the you find a probe in the indicator probe folder so that you were able to monitor the state of your clock input, and as well as the state of all the 4 binary coded decimal digital display lines. Once you insert one of these indicators, you're going to have to double click on it and then change it from 2.5 volts to 5 volts, because they nominally come in 2.5 volts. And in the end, your circuit should look something like that, except for your 555 timer will look like this, except for it'll be 555, virtual. Well, we hope you've enjoyed the show. Thank you so much.